Chapter 4B, Hypothesis Testing. So we're going to now develop our methods for investigating a claim and determining if there's enough statistical evidence to support our claim. So make sure you read through why, our learning objectives for this activity, and the vocabulary. And so example 1 is an introduction to hypothesis testing. So now we have our method for analyzing data. We're going to set up hypotheses to test our theories and claims using our normal distribution like we have in earlier parts of Chapter 4. So last week, Professor Caldwell told me that she believes LMC students enroll in more units than the California Community College average of 12 units. How can we test this claim to see if it's true? So we set up the following study to test the claim. So our claim is this question here. Is the average LMC student enrolled in more than the California Community College average of 12 units? So we first write a null hypothesis. Null means nothing, so we say the null hypothesis represents no change. We use H and then a 0 down here. The 0 is standing for no change. So the null hypothesis here says the average number of units for LMC students is equal to the California Community College average of 12 units. So we're saying here the mean equals 12. And we're talking about the population mean, so if we were going to write this symbolically, we would use mu. We would say mu equals 12 is our null hypothesis. The alternative hypothesis is where we analyze our claim. So it can be written H1 instead of H0, or HA is what we'll commonly use. And so that says the average number of units for LMC students is greater than the California Community College average of 12 units. And so this claim comes from what Professor Caldwell believes, that LMC students enroll in more units. So this is why we're using the greater than relationship. What is the claim? The alternative hypothesis corresponds to the claim, which in this case is that LMC students enroll in more than an average of 12 units. So in the null hypothesis, what are we assuming is true about the population? So the null hypothesis always has equality in it. So in this case, we assume the population average, or the population mean mu, equals 12 units. So in the alternative hypothesis, how are we comparing the true parameter, which I drew a note here that this is mu, the mean, that we don't actually know. So how are we comparing the true parameter value unknown to us to the value that we assume is true? So we're saying in the alternative that the LMC mean is greater than 12 units. So here's some general observations about the null and alternative hypotheses. They are competing claims, so they can't both be true at the same time. And they're about the population parameter. So when we say the mean equals 12 units is our null hypothesis, then the alternative hypothesis that the mean is greater than 12 units is a competing claim because you couldn't have both equal and greater than 12 units for your population mean. They're both statements about the same population parameter. So they're both talking about that same population mean units of California Community College students and LMC students. And the null hypothesis always contains an equal sign. And the alternative hypothesis is always an inequality. So it could be less than, it could be greater than, or it could be the not equal to symbol. And in a statistical investigation, we have to first determine the research question and then the hypotheses before we go collect data. You don't want to be a researcher who collects data and then tries to backtrack and form hypotheses. That wouldn't be authentic research. So we've got 4 steps to our hypothesis testing process. You might want to pause and read through this more slowly. Step 1 is what we just looked at, determining the hypotheses. Step 2, we collect the data. In our packet examples, we're either going to be working with a data file, or I'm going to let you know, here's the data the researchers collected. If you do a project, you'll have the option of going out and collecting out your own data. Step 3 is we assess the evidence. So we always start by assuming the null hypothesis is true. We look at how extreme the values are and think, could the data have come from the population we're describing by the null hypothesis? And then step 4 is that we state a conclusion. So there's 2 possible outcomes. So one possibility is that the results are similar to the actual that results similar to the actual sample are extremely unlikely. So that would tell us the data does not fit in with the results from random samples. The other possibility is that the results that we get from our data are fairly likely or not unusual. So we're going to see both of these ways of analyzing the outcomes. Hypothesis tests can be one-sided or two-sided. So if you're setting your hypothesis up like this, the null hypothesis is that the mean equals 0, and the alternative hypothesis is that the mean is less than 0, you're going to be working strictly with p-values, probabilities, in the normal distribution over on the left side of the graph because we're strictly looking at means less than 0. So that would be values out here. Similarly, you could have what we call a right-tailed p-value if you have the greater than inequality. What if you have mu is not equal to 0 using the not equal to inequality in your alternative hypothesis? Then you could have less than or greater than, and so you have what we call a two-tailed p-value. So the p-value is the probability of getting results like the data that we had, assuming the null hypothesis is true. So remember, we're always assuming the null hypothesis is true, and then we're going to say how likely are the data results that we have here. So here's some scenarios where we're going to write null and alternative hypotheses and explain if our test will have left-tailed, right-tailed, or two-tailed p-values. So in question A, we've got blindfolded participants. They're taking a taste test. They're rating the sweetness of Coke drinks on a scale of 1 to 5. And the scientists planning the study claim that the average sweetness rating for Coke is going to be more than 2. So our null hypothesis always has equality. Here I've written it with symbols. If you want to use words to write your hypotheses like we did in the previous example, that's fine also. So here for the null hypothesis, we say H sub 0 for null hypothesis symbol, colon, is that mean equals 2. And this mu is the population mean, not the sample mean. The alternative hypothesis, H sub A, colon, is that the mu is greater than 2. This would be right-tailed because we'd be above the mean on the right side of the graph. Part B, a professor is comparing the average statistics midterm exam score for her class to the average midterm exam score of all statistics students last semester, which is 0.76. The professor believes that the average statistics midterm exam score from her class will be significantly different from 0.76. Since she is saying significantly different, not less than or greater than, we use the not equal to inequality. So our null hypothesis, H sub 0, is that the mean equals 0.76. And the alternative hypothesis, H sub A, is that the mean is not equal to 0.76. So this is a two-tailed hypothesis. It could be that the mean is less than 0.76, or it could be that the mean is greater than 0.76. So let's look at how we would conduct a hypothesis test for one mean. Here is a data set with information from a sample of 931 homes about rents in San Francisco. This comes from a random sample of rents in December 2016. So the sample mean is $2,017 per month, and we can assume the standard deviation is known to be $1,600 per month. So here we see, here's our X bar, our sample mean 2017, our standard deviation. Since it's known for the whole population, we use sigma here. And then N is 931 homes, our sample size. A real estate specialist tells you that the actual population mean is $1,900 per month, but your cousin claims that the mean rent is actually higher. So let's investigate this claim of your cousin's. So when we set up our hypothesis, remember the mu equals 1900 and the null hypothesis is assuming equality. So here we're assuming the real estate specialist is correct about the population mean. Your cousin's claim is that the mean rent is actually higher than 1900, so here's our alternative hypothesis. This is a right tail alternative hypothesis because it's greater than and it's one-sided, so we expect unusual results to be on the right side of the graph. Our next step is to collect the data. So we have the data already collected for us. So we want to make sure that the normal model is appropriate for this data that's already collected for us. So the first thing we check is the sample size. the sample size n equals 931 is greater than 30, so we assume that this distribution is going to be fairly normal, so that condition is met. The data is also from a random sample of rents in December 2016, so the condition that we have a random sample is also met. So these two criteria are met, and we're able to go about applying a normal model. So now we're going to go in StatCrunch and let StatCrunch do a z-score calculation and plot out the p-value for us. So this is one sample we're looking at. Since we know the population standard deviation, that sigma is 1600, we're going to use what we call z-stats because we're using a normal model. So let's go into StatCrunch. And I'm going to go to Stat, z-stats, one sample, and then with summary. With data would be if we had a whole data file here with an entry for each apartment. So our sample mean is 2017. Our standard deviation is 1,600, and our sample size is 931 homes. And then we're comparing our mean to $1,900, and our alternative hypothesis is that the mean is actually greater than $1,900. And then I check the p-value plot down here because I want to see the normal distribution graphed out for me. So this first window here is giving us the hypotheses written up here, and they're telling us this is the mean you're calculating for, the population mean mu. We know n is 931. We know our sample mean is 2017. StatCrunch calculated the standard error for us using the sample data, so that's much easier than having to calculate it on our own with a messy formula. And then they found the z-stat and the p-value. So if we arrow to the right, we can actually see here's the normal distribution. So assuming that the graph were centered at 1900, we would be more than 2 standard deviations away with a sample mean of $2,017 rent per month. So the p-value here is 0.0128. So remember that the z-stat, also known as the z-score, you'll hear me refer to it both. I think StatCrunch calls it the z-stat and your textbook calls it the z-score, but they're talking about the same value there, is a count of how many standard deviations the statistic is from the center of the distribution. So based on the z-score and the normal distribution plot, does the statistic seem significantly far from the center of the distribution? So let's go back and look at our normal distribution plot. It's more than 2 standard deviations away, so it doesn't look like it's too close to me. So we say since our statistic, the sample mean 2017, is more than 2 standard deviations from the center, we think this result is unlikely if the population mean rent is 1,900. So how do we make a decision? How do we assess this evidence based on these results? So a small p-value indicates that it's unlikely that the actual sample data came from the population described by the null hypothesis. So in this case, our population is the mean rent is $1,900 per month in San Francisco. More specifically, a small p-value says that there is only a small chance that we will randomly select a sample with results at least as extreme as the data if the null hypothesis, h sub 0, is true. The smaller the p-value, the stronger the evidence against the null hypothesis. So in this scenario, if the population mean rent really is $1,900, there is only 0.0128 or 1.28% chance that the average rent for 931 homes would be 2017. So notice we're assuming the null hypothesis is true and saying what's the chance of getting an average like this from a random sample. So in practice, we typically compare the p-value to 0.05. All right, and the reason for this is because Ronald Fisher in 1926 said, hey, 0.05, that's about 5% room for error. Let's use that value. Nobody has objected to it since then. You could use 0.04 or 0.06, but our default is going to be 0.05, which leaves 5% error. And his reasoning was 1 in 20 corresponds with a 5% error. So statisticians use 5%. There's no magical reason we use 5%. You could certainly use 4% or 6%. You'll see sometimes we use 1% as a point if we want to be very sure. So when the p-value is less than or equal to 0.05, when our results are unusual, we say that the difference between the actual sample statistic and the assumed parameter value is statistically significant, meaning there is some difference here. So does the p-value from this hypothesis indicate that the difference between the sample statistic, $2,017 per month, and the parameter value, $1,900 per month, is statistically significant? It does. Our p-value, 0.0128, is less than 0.05, so we do say that this difference is statistically significant. So now we want to think about how do we state our conclusion. So if the p-value is less than the significance level, as in this example, we reject the null hypothesis and accept the alternative hypothesis. The other possibility would be that our p-value is more than that 0.05, in which case we fail to reject the null hypothesis. We don't get to say, null hypothesis, you're certainly true, and accept it with open arms, but we can't reject it. So we say there's not enough evidence to support the alternative hypothesis. We never get to say the null hypothesis is definitely true. And I put a note here, it does not say the null hypothesis is true. So let's state our conclusion. So our results show a statistically significant difference between the assumed parameter, 1,900 rent, and the sample statistic, $2,017 rent. We reject the null hypothesis. It is unlikely that the population mean rent is 1,900. We accept our cousin's claim that the population mean rent is greater than $1,900 per month. So we let StatCrunch do our calculations, but you can also calculate by hand. So here is our z-score formula. Remember, it's the statistic minus the parameter, that's the population value, divided by the standard error or the standard deviation. So in this case, our statistic, because we're dealing with quantitative data, is x bar, the sample mean. Our null value is what we analyze in the parameter. And then our standard error is going to be sigma divided by square root of n, since we're sampling. So if we put our values in, we have 2017 minus 1900 in the numerator. That's 117. And then our denominator is 1600 divided by the square root of 931, which is 52.4. And when we divide, we get 2.23 standard deviations. That's really close to StatCrunch. If we look back at StatCrunch, StatCrunch was 2.2312. So we rounded our calculations right around here. So that's why it's a little bit different, but basically the same, give or take rounding. Then we want to figure out, well, what's the probability that z is less than 2.23? So you could go to the normal calculator or your chart back on page 129 and get that the value less than 2.23 is 0.9871. Let me show you in the normal calculator how we could do that. So you can go to Stat, Calculators, Normal Calculator, and figure out the probability less than 2.23 standard deviations. And this is where that 0.987 is coming from, give or take rounding. And the probability that our z-score is greater than that 2.23 standard deviations, well, we say 1 minus 0.9871. And so that's 0.0129, which is an exact match for our p-value that we got from the normal distribution. So, if the null hypothesis is true, how often should the p-value be less than 0.05? 5% of the time, or 1 out of 20 trials. So this is happening at a smaller rate there, right? We're saying if the null hypothesis is true, this would only happen about 1% of the time. So suppose instead of using 5%, we used a 1% significance level, in which case alpha would be 0.01 in the San Francisco rent hypothesis test. Would the evidence have been strong enough to reject the null hypothesis? So our p-value was 0.0128, which is greater than 0.01. So at the 1%, or alpha equals 0.01 significance level, our result is not statistically significant. The conclusion would change. So if we were conducting our hypothesis test at the 0.01 level, we would fail to reject the null hypothesis. So there's not evidence at the 1% level to support our cousin's claim. So a researcher determines their significance level before they conduct their study. You don't want to be manipulating your significance level based on your results. That would be unethical. Typically, a 1% level is used for something like medical research where we need to be very precise. Something like a political survey might use a 10% level where you don't need to be as precise. So we see it is possible to make the wrong conclusion in hypothesis testing. So there are two types of errors that come up in hypothesis testing: the false negative and the false positive. So here's a helpful diagram to show us when these types of errors are. The first possibility is that the null hypothesis is true, but we reject the null hypothesis. So that error is called a type 1 error or a false positive. If the null hypothesis is true and you keep the null hypothesis, meaning you fail to reject it, that's the correct conclusion, so that's not an error. The other type of error that can occur is if the alternative hypothesis is true, but you keep the null hypothesis. So that's what we call a type 2 error or a false negative. So consider a company marketing a computerized medical diagnostic program. What are the two hypotheses and the two types of errors that could happen with this computer program? So the null hypothesis is going to say that there are no change in the patient or that there are no medical problems. The alternative hypothesis is going to come back that there is a change or there is a medical problem with the patient. So the false positive is going to be that the patient has no medical problem, but the test says they do have a medical problem. The false negative is going to be that the patient has some medical problem, but the test is coming back as no problems. So if you could adjust the program to decrease one of these probabilities, what do you think should be made smaller? Which error? And so this is an opinion question, but my opinion is that we should decrease the probability of the false negative, that's the type 2 error, even if this increases the false positive rate. And my reasoning is that we don't want people spreading diseases or being sick without treatment.